cycling for them. If you have an exhaustible resource, it's like having a big pile of coal, oil, chocolate bars, whatever. And your problem is, how do you take them out of the pile? How do you take the chocolate bars off the pile and eat them across your lifetime? How do you take the oil out of the ground and burn it across time? So it's allocating a stock, a big pile of stuff, to different time periods. That's the fundamental problem with an exhaustible resource. With a renewable resource, the problem is how to get a sustainable flow out of the resource. So, for instance, you could be the United States and in 1976 have taken over the waters as an exclusive economic zone out to 200 miles and chased all the other fishermen out of there, and then bought your own fishermen so many boats that they completely destroyed the fish stocks and there were no fish. That's probably not the right management scheme. That's the management scheme we chose, but it's not the right one. The problem is, having established the exclusive economic zone, to have chosen ways of harvesting and amounts of harvesting that would keep us in the fish business essentially forever. That was the issue. So more fish are being created, and in order to get a steady state, you have to take the fish out at about the rate they were being created. And that's a sustainable management. Okay? So they have very different feelings, too. If you have an exhaustible resource, sustainable management is impossible. It just can't be done. The pile gets smaller every day. There's nothing you can do about it. You can find something else to do instead eventually, but an exhaustible resource, you just have less of it all the time. It's purely exhaustible. A sustainable resource, renewable resource, the trick is to take it out in such a way, to use it in such a way that you always have stuff left and that you can keep doing it for a very, very long time, like forever. Static efficiency. So supply equals demand. You've done that a couple times? Yes? Did you do something where you did consumer surplus and things like that? Yeah? And when supply equals demand, you get the maximum of willingness to pay plus profits? Yeah, that sound familiar? That's static efficiency. You have one time period. Your model is you wake up in the morning, you do some sort of work, you take the money, you go to the grocery store, you buy some stuff, you eat the stuff, you die. World's over. You don't have to worry about tomorrow. Because there is no tomorrow. Right? That's a static efficiency. If you're going to talk about natural resources, it's not going to make any sense. Because the exhaustible resource problem is fundamentally a problem of how much do you take today and how much do you take tomorrow? Well, there is a tomorrow. Well, if there is a tomorrow, you can't have a model in which there's no tomorrow. So the static efficiency model in which you just have one day, demand equals supply, and we're all done, that's not going to work. You know how to find static efficiency by now, I presume. You equate the marginal cost of producing the good with the marginal benefit of producing the good. And marginal benefit is otherwise found how? It's price, is it not? So you go to the demand curve, and you ask, what would the consumer be willing to pay for one more unit? In the simple case, all there is one consumer. There's no externalities. There's nothing interesting going on. It's the point on the demand curve is price. That's marginal benefit. You get price equals marginal cost, and you're done. There's no time. Okay, dynamics. You have more than one period of time. Once you have even two periods of time, call it dynamic. Now you have to do the same thing, but you got to do it 2 days in a row. In less than a toy model, you got to do it an infinite number of days in a row. But let's go for the toy model. So how do we find it? Well, therein lies the tail. So we have a very particular resource in mind. Right? So what we have in mind is a pile of coal. Right? And it's going to have some cost of taking it out of the pile. The pile will never get bigger. And so any coal I don't take out of the pile in the first period, I can take out of the pile in the second period. That's the thing that drives this model. So you have a way of getting coal from the first period to the second period. All you have to do is just leave it sit in the pile. It's easy. So that's the added piece to this. So you have a choice of taking it now or taking it later. Right? It's a one-to-one trade-off. Every piece you take now, you can't take later. Every piece you take later, you can't take now. So what would characterize efficiency in a world like that? Well, if I take a piece now, what's the benefits? It's whatever the marginal benefit is from one piece of coal minus whatever the marginal cost is of getting at that one piece of coal. If I take it out next period, it's the marginal benefit in that period minus the marginal cost in that period, but there's one more thing I have to do. What was your last problem set I saw on the table? What was the problem set about? I thought it was discounting. Didn't you have a discounting problem set? Yeah, present values. Okay, discount. So what do I have to do to the value in the next period? Do I have to discount it? Yeah. So in order to get efficiency, it's marginal benefit minus marginal cost in this period. That's the benefit from doing this period. The benefit from doing next period is marginal cost minus marginal benefit, all of that discounted. Like I said, the two equal. So the idea is to take just enough coal in each period, so marginal benefit minus marginal cost is the same in both periods. The second period was discounted. Clear enough? That's our way of getting efficiency. By equating present values of the marginal net benefits for all periods, as many as they may be. Time is a factor, hence the discount rate. There are two time periods. Yes. Demand. Marginal willingness to pay. We have a demand function we're going to work with. So we're going to work out a little two-period example here. And it's not going to work out quite in integers, but we'll do our best. Marginal cost is constant and set equal to 2 if I remember right. Yes, there is 2. Right? So now we have the elements of our model. We have marginal benefit minus marginal cost. So marginal benefit is P, is 8 minus 0.4Q, minus marginal cost is 2, or 6 minus 0.4Q is marginal benefit minus marginal cost. Same in both periods. Yeah? So we'll have a downward sloping line in a minute. So suppose there were a lot of this stuff. Suppose there were like 100 units of this stuff. Actually 30 or more the way it works out. So let's think of what could happen. So marginal benefit minus marginal cost equals 0. What quantity does that happen at? You can come back and look at this. You can say the second on it. So take P minus MC, set it equal to 0, and tell me what Q is. Right? Someone can do that algebra for us? Is anyone fast at this stuff? What, 15? That's what I get to, I agree. So it's 15. So let's suppose you have 2 periods. What's the most stuff you could use in 2 periods? First, what's the most stuff you can use in 1 period? Suppose there were 16 units available, and you had only 1 period. Would you use them all? Or just leave some of it? Any thoughts? I know that price minus marginal cost, price from the demand curve minus marginal cost is downward sloping. You agree with that? That's marginal benefits from taking something. The marginal benefits hit 0 when Q equals 15 because a friendly algebraist has told us that. So would you want to take 16 if they were there? Anyone want to take 16? Anyone want to stop at 15? How many want to stop at 15? Yeah, well, that's good thinking, right? So if you had 2 periods and you had 30 units, would you take them all? Yeah, you would. But if you had 31 units, would you take them all? No, right? So if you have 30 or more units, the overtime thing isn't going to matter very much. There's so much of stuff you don't know what to do with it. Can you think of a resource for which that's probably true? Do you think that's true of oil? Do we fundamentally have so much oil we don't know what to do with this stuff? No. What about coal? Do you think we fundamentally have so much coal we don't know what to do with this stuff? Who says yes? Who says no? We have like hundreds of years worth of reserves of coal that we know about already. If you do the calculation, you'll discover before you can use all that coal, you're not going to have an atmosphere left. So the coal in the ground probably doesn't have much value. Right? There's plenty of this stuff. It's not to say that a high-grade deposit near the surface that burns really well is not worth money. But if you're asking about the last little bit, it's probably not worth anything. So now we know if we have a lot of stuff relative to the size of the market, the stuff itself isn't worth anything. Let's just go back through that example again. Let's suppose it's 15 units, it's 1 period. Suppose there are, 15 units is the most we can use in 1 period. Let's suppose we have a 1 period model and 16 units of coal. How much would you pay for a unit of coal? Before it was extracted. Before you did the $2 worth of work to get it out of the pile. What's it worth before you extracted it? How much? Any ideas? It happens to be too much of something. It's going to be worth a lot or a little. A little. It's going to be worth 0. Right? Because when you do price minus marginal cost, right? Price from the demand curve minus marginal cost equals 0. So if someone charged you money for the coal, you would just lose your money in that setting. So it's 15 or more units. The coal itself has no value. In order for the coal to have value, you have to have less than 15 units. If you had 10 units, right, you could work out what's price minus marginal cost. Now it would be a positive number, would it not? And so if you had a unit of coal, you could earn that amount of money. So the coal would be worth price minus the marginal cost of extracting it. So it could be worthless. Coal in the pile could be worthless if there's a lot of it. But if there's not a lot of it, then price minus marginal cost of extraction, positive number, equals the value per unit of coal in your pile. So it can be valuable or not valuable, depending on how much. So let's, right. So now here's our downward slope. Here's marginal cost equals 2. So remember that's P minus 0.4Q, or 8 minus 0.4Q. AP equals 8 minus 0.4Q. Do I remember right now? That's the downward sloping line. Price equals marginal cost at 15, just like we calculated before. So if there were 15 units, price would equal marginal cost. Price minus marginal cost would be 0. There'd be no money left to pay for the coal itself. Remember, MC is the cost of taking it out of the pile and getting it to the consumer. Here's the second period. And so obviously if both periods are the same and you have 30 units, you're done. Now suppose it's scarce. Now what do you do? Well, the present value of a 2-period model is the sum of the present value in each of the periods. All right, that makes good sense. And what is the new condition you get? The value of taking coal in 1 period equals the present value of taking coal in the other. Price minus marginal cost in period 1 equals price minus marginal cost divided by 1 times plus the discount rate in period 2. Same present value whether you allocate coal today or you allocate coal tomorrow. Yes? Tell me when I should move on. Right. PV is present value. MNB, marginal net benefit. MNB is price minus marginal cost. So it's the present value of price minus marginal cost in 1 period relative to the other. Price period 1. Right, that's what that bottom line says. This is what we call it, marginal net benefit. And right, the line. And then if you wanted to stay algebraic, you'd remember that price is a function of quantity in period 2, and price is a function of quantity in period 1. Right? And if I were going to close the model very quickly, I would say the total amount of stuff equals, okay, that's the model algebraically. Did I give you another minute? Is that wanted? That's a cool idea. I never thought about it. Well, when I do this in the fall, I bring my own machine and I can write. I have a stylus, and then we record all the slides, and so you would, instead of writing on the board, you'd have it. But I like the cool idea of using the camera to capture the board. Okay, so let's move on. No, I'm moving on. Yeah, total resource constraint. So here, in terms of the way I wrote this, let's just substitute. Maybe I should get rid of the word Stan. That's not helping us. Sorry, Stan, but you've been erased. So here's where the 20 goes. The total resource constraint is 20. The interest rate is 10. 10%, right? So this number becomes 1.1. So when you see 1.1 in the algebra below, that's where it's going to come from. Demand curve is as before. So both of these demand curves are, this is P equals, 8 minus 0.4 Q1, and MC is going to be 2. So equals to 2. Okay? So now we have all the pieces. And ditto over here, obviously. P2 is a function of 6. Yeah? We got the model down? Now we have the model with all of its parameters in it. And let's see what we can do with it. What am I? All right. So start with a curve that starts at 6 and comes down to 15. What is that? That's this exactly, right? That's literally 8 minus 0.4q minus 2 as a function of q. Literally, that should say quantity in period 1, and it does. So the vertical axis on the left is the, no, there are two axes on the bottom, right? The one that counts upward, 0, 1, 2, 3, 4, 5, going in this direction, goes with the curve on the left. Okay. The vertical axis on the curve on the left is dollars per units, price, and it's literally P minus MC. Now let's look at the one on the right. The right has, as it's counting, going that way. Starts at 0 and comes over here to my right, your left, right? Counts in that direction. It's the same curve with one exception. Everything got divided by 1 plus the interest rate, 1.1. And that's why instead of being 6, it hits at 5.45. I'm sure if you divide 6 by 1.1, you'll get 5.45. And then it hits at 5. And I haven't done the algebra to prove that's right. So now I have the marginal net benefit, right, for period 1 and the present value marginal net benefit for period 2. And what does my equation say to do? It says set them equal. So I find where the two curves cross. That's the dotted line there at approximately 10. So reading for the quantity in period 1, it's a little more than 10. Reading quantity in period 2, it's a little less than 10. 9 and a big fraction. So can you read that graph? Or do we need to say more about that? Has Gordon done these two-headed graphs before? Yeah, we like two-headed graphs. So now we have a solution. And in our solution, the marginal present value benefit of taking some of the resource in each period is the same. That's the solution concept. Same marginal benefit, present value. I'm going the wrong way again. Let's go to 19. Here we have exactly what I wrote on the board, right? So if you copy the board, don't copy this. It's the same thing. Except by writing it on the board, I was able to make the fraction have a big line rather than a little one. So I have two equations. So far, there are two unknowns. Yeah, Q1, Q2, yes. And now we have the adding up constraint. Q1 plus Q2 equals the total amount equals 20. So now we're in business. So now we can solve this thing down to the final answer. And he gives the algebraic solution as 10.238. And you obviously can calculate the other one very easily. It's 9.762, right? I do my algebra in my head fast enough? You know I was able to do that, right? Because they had to 20. I didn't do it the long way. Trust me. So that is the algebraic solution. Your questions? You want me to walk through that again? I just move on if you don't stop me. It's okay. Okay, I assume that's okay because you haven't said anything. 762. Right? And that's the same thing you read off the graph. Nothing else. How do you find P1 and P2? Well, that's actually the easy part. Let's see if we get an equation. Well, if I wanted P1, I would just say, hey, wait a minute. P1 equals the point on the demand curve, 8 minus 0.4 times Q1, and Q1 is 10 point whatever, right? I just solved that. That's all he says to do. That's all you have to do. So once you have the quantities, you can just look up to the demand curve. Let's go back. It's going to be pretty interesting. See how well it's done. All right. So once I have that quantity, 10.2 blah, 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 I can read up to where the demand curve is and then read over, and the answer is $1 and some. Do you agree? It's approximately $1. I'm looking at the quantity 10, and then what I need to do is I need to be able to go from that quantity 10 up to the demand curve, the one that comes down from 6, and then come across, and I presumably will get 1 and something. Is that right? All right, I can assume it is. I'm sure it is. And that's all that's happening in the algebra. There's your algebra. 3.905. I go back and look at that graph more carefully. The graph is not well drawn, if that's right. And here's P2. And that's from the algebra. Do we think that's about right? Yeah, it should be about 10. It should be about 4. Yeah. Oh, why did it not work when I did it on the graph? Someone can tell me that? I understand now. What was it on the graph? Well, the problem with the graph is price minus marginal cost. And so what I solved for, that's 1 and a little, is price minus marginal cost. I had to add the marginal cost back in. I had to add the 2 back in. And then I get this. Yeah. But the reason why what I did doesn't work is I didn't add in the 2. That's right. And you could now actually find the net benefits. The net benefits are the area under the demand curve, right, and above marginal cost. So these aren't really shaded well. Let me again draw on the board again. So, well, maybe it is. This is right. Okay. There shouldn't be a. It's 2.